Fantastic. Thanks very much, Steve. And good afternoon, everyone. I'm Mark Nicholson. I'm one of the founders and the CEO of Vivacity. I want to talk to you today about a very specific technology use case, trying to draw together some of the ideas that we've already heard around how do you get different kinds of road users to feel like first-class citizens on the road. How do we design the infrastructure to support them? And in this case, I'm going to focus in on active travel, so cyclists and pedestrians, and how do we help signals to support those road users within the road environment. So I wanted to introduce this through the lens of two fictional characters. Beth, someone who's just starting commuting in towns for the first time, trying to cycle around, but not necessarily getting on with the urban environment. And Nathan, a new dad during the pandemic, who's now just starting to take his child out on the roads for the first time. And so, looking at a specific example, I don't know how easy this can be seen, it looks quite dark here, but specific example of having someone come up to a junction, so cyclists coming up from the bottom, how do they actually get detected as they come up to that junction? This is a junction that I cycle through most days, and I know that the induction loops are off-center, they won't detect me as a cyclist, and so that cyclist pulls up, isn't seen by the junction. Pedestrian joins, they might push the pedestrian button to wait for the signal, but the junction still has only a very crude understanding of the cyclist and the pedestrian in that environment. And that leads us to the first challenge from an infrastructure perspective for adapting to these users. It's all about detection. And we see detection going through a series of sort of different levels. First level is presence detection, that's your pedestrian push buttons, that's your induction loops. Beyond that, you start to get to a level of classification because cyclists and e-scooters, for example, behave differently. They behave differently to motorbikes. But they're actually all quite similar sizes of road users, but they will accelerate differently through the junction, and so the junction should treat them differently. Then you get on to factors like number of pedestrians. You might have one person stood there who'd press the push button, but you might also have a football crowd, or it might be the end of a school day. Trying to adapt to that number of different road users trying to cross, again, means that the junction should behave differently. The final sort of layer on this is then about behavior. Nathan from earlier, if he was walking his young child around, he's not going to be very quick crossing that road. And so the junction should adapt to that and give him the right amount of time. So in order to make our infrastructure actually adapt correctly to these road users, it needs to gather all these different kinds of data and feed them into signal control. So this is something that we've been working on for the last few years. I won't spend much time on the video. One of my colleagues went through some of this yesterday, and we've got a stand over there to see more. But the point being, gathering better data, in this case through computer vision, to classify different road users, understand how they're moving, is a critical foundation for making the infrastructure more reactive to these kinds of road users. So we've got to the point where the junction now knows that they're there. But looking at the movements they might want to do across the junction, if the cyclist wants to go all the way across this fairly large 5-arm junction, it takes quite a long time. And if she were to go through on amber, the other roads would turn to green before she gets off the junction. Similarly, looking at the pedestrian, if he wants to cross diagonally across the junction, he actually has to cross twice. And that's something that's probably going to take him 2 cycles in a lot of current setups. So next question is then, how do you solve for prioritization of these different road users within this junction environment? Again, much like detection, we see a series of different levels of capability of prioritization. Unfortunately, a lot of current systems have no action at all for these road users. Cyclists are often ignored. Pedestrians, if you're lucky, the push button will do something. If you're not, as you know, it's often a placebo. Next level up is then giving them some kind of time allocation. So that this is what the pedestrian push buttons are. It's making sure that, okay, they get some time within that stage. Fine, we feel like we've dealt with them. But what we haven't done is we haven't treated them equally. We haven't given them equivalent priority to the cars. We haven't looked at, okay, well, but how many pedestrians are waiting there? If there are 100 people waiting there, shouldn't we cut short the car stage to allow the pedestrians through? So there's then a question of equal treatment based on the better data that we can gather. Final stage is then thinking about prioritized treatment. Active travel is a huge theme for authorities all over the country, we don't just want to treat them equally. We want to actually say, on some junctions, at certain times, they should have priority. They should have a higher weighting. And so there's a whole range of different levels of prioritization that you can look at in order to get to a world where cyclists and pedestrians feel like first-class citizens. And all of this needs to be done in a world where you're not trying to reduce the overall throughput. You don't want your cars to be complaining that you're prioritizing the cyclists and pedestrians. So you need to think about how do you balance all those different elements. So we've got quite a complex system. You've got a system which is trying to prioritize based on weights, rather than it being just a binary on and off, there's some pedestrians there or giving them some time. You need a system that leverages the rich data that we've just been talking about, that if a pedestrian is slow across the road, can actually make use of that insight. And one that adapts to the huge complexities of the real world. A system that allows you to look at different kinds of junctions, different sizes of junctions, and it acts fundamentally differently as a result of those. You bring these different elements of complexity together, and you're looking at something that's so flexible, you kind of have to be in the world of AI. You're starting to get to a level of data inputs that only AI is able to solve. So this is what Vivacity's been looking at for the last couple of years. How do you use AI to address all of these challenges? Now, the first time that you try to deploy an AI to solve this kind of issue, it's a little bit like putting a child in charge of a traffic signal junction. They will change the lights randomly, they will make random actions because they don't really know what they're doing. So before you can try to deploy AI in this scenario, you need somewhere to train it. You need somewhere for it to grow up. So you actually start off with simulation, you build detailed simulations of the junction, use that to train your AI to give your child time to practice. And that child needs really quite a lot of time to practice. So many of the people in this room will have 10, 20 years of signal experience. In order to get this child to sort of a level of competency, we need to get it to not just being an old man, but actually we've given it 2,000 years of experience. That's probably the collective traffic signals experience of everyone in this room, focused in one AI to control the traffic signals. And that's the level of capability that you need to be able to adapt to that huge flexibility in the real world, to be able to take all those different kinds of inputs and get to a good result. So using that kind of capability, we've now deployed in various junctions, mostly in Manchester. And I want to talk about one of the outcomes of that from the point of view of looking at stage timings. So existing systems, there was a PED stage which had a relatively short amount of time. It was given about 18% of the time at that junction. And thinking about what I said earlier of time allocation versus equal priority, when we then deployed AI with equal weighting to say, okay, pedestrians are now equal to cars, we found that actually it substantially increased the amount of time that it gave to those pedestrians. So now that stage is up at 25%. When you start then adding in prioritization for pedestrians and saying actually they're more important than cars, it shifted it further up into the low 30s. So the point being that the existing time allocation-based systems weren't getting to a world of even equality, never mind prioritization for those pedestrians. So you've got your cyclist and your pedestrian. They're feeling happy that they've now been detected by the junction and they've been prioritized to some degree by the junction. You've got a level of evidence that, yeah, okay, there's now more time on the pedestrian stage. But many of the people in this room will be engineers. There'll be that demon sitting on your shoulder going, but prove it. How can you actually demonstrate that this has really, really worked? And so that's the next problem from my perspective, because many of the existing systems, the only level of proof that we've got has largely been through expert observation. It's been through people going out to site, looking at it for a few hours and going, yeah, that looks like it's behaving sensibly. I believe in what that's doing. But from a sort of analytical, academic point of view, that isn't particularly comprehensive or compelling proof. You need to go way beyond that. So the next stage is then to look at A/B testing. Look at, okay, over the course of a month, a couple of months, we're going to do one day on, one day off. We're going to switch the systems up. We're going to really prove the difference between these two. That's great, but it's still only one site. And doing that at large scale is actually quite challenging. So where do you go from there? Well, in order to do sort of larger scale benchmarking, you then need to think about how do you simulate this so that you build something that's academically robust across a huge range of different sites, so that when your AI child is not just 2,000 years old, but 3,000 years or 4,000 years, when it's continued to evolve, you can then actually check its ongoing performance. So you don't just have a point in time, but so you have something that can keep adapting to new technology coming into the space, to new suppliers coming in, new algorithms. You need something where you can continuously benchmark and baseline. This is the way that the likes of Google and Facebook train their algorithms. They build huge-scale simulations to test things and to be able to retest and iterate. And that's what we as an industry need to get to as well, the point where we can benchmark at scale. So from the work that we've done so far, we haven't got to that point. We are not yet benchmarking at scale, something we'd love to do. I'll come back to that in a minute. But we have done A/B tests. So what you're seeing here shows the average journey time for both us versus the incumbent system over just over a month's worth of A/B tests, where we demonstrated that we were, on average, reduced journey times by 23% over the course of that period. So we've demonstrated that AI can control signals. It can control signals effectively. The incumbent system here was Scoot. There are various caveats for why we may or may not fully believe the results here. This is why we need to keep scaling this up and demonstrating it in more areas. Nevertheless, first proof that AI works to control traffic signals, and it works better than the Scoot system in this location. So where are we going now as a business? We started doing this work in Manchester. We've done similar work just on the detection side in Sheffield and Leeds. We're now rolling out this full system to Cambridge and Peterborough as well. So we're gradually rolling out the AI for signal control capability across the country. Our sensors are in many, many more cities than that, but on the signal control side, we're currently working with 5 cities. So we've got to the point, we've proven detection, we've proven prioritization to some degree with that time allocation, but we need to go further. From a proof perspective, we've demonstrated the A/B tests, but we need to go further into scale benchmarking. So where are we going now? 2 major next steps. 1, we're launching an early adopter program to test this in many, many more cities. So if you're interested, please come talk to us afterwards. And 2, we're trying to scale up that benchmarking piece. We're trying to get to a world where we have simulations of many tens, ideally hundreds of junctions, where those are then run through an open source system so that anyone can see how those are going, so that as an industry, we have better baselines to be able to compare our signals on. So if you're interested in talking about that as well, please come talk to us afterwards. But otherwise, that's largely it from me. Just wanted to say, by doing this kind of thing, we'll get into a world where both cyclists and pedestrians can use the traffic signal network much more effectively and can be much more comfortable and treated as first-class citizens. Thanks very much.